Welcome back to Fundamentals of DC Circuits. In this video, we're going to discuss the maximum power transfer theorem, as well as delta to Y conversions and Y to delta conversions. The learning objectives for this video are that you will be able to understand and apply the maximum power transfer theorem, as well as to perform a delta to Y or Y to delta conversion. So let's begin with the maximum power transfer theorem. This theorem states that for a given source voltage, the maximum amount of power that will be transferred from the source to the load will happen when the load resistance is equal to the internal resistance of the source. So let's say that you have a DC power supply that has a certain amount of internal resistance. And then you'll connect some sort of load to that power supply, some sort of resistive load. When we think about the maximum power that will be delivered from the source to the load, that maximum amount of power will occur when the load and the source have the same amount of resistance. And we'll prove this by example. So let's say that the source below has an internal resistance of 75 ohms. We're going to determine the power that is distributed to the load for each of the following values of resistance. We'll start with a load that's smaller than the internal resistance. Then we'll do a load where it's equal. Then we'll do a load where it's larger. What we're going to see is that the maximum amount of power that the load will have will occur when the load is equal to the source resistance. So let's begin with assuming that we have a load of 50 ohms. And we want to just simply determine the power for the load resistor. To do that, first we'll figure out the total current in this circuit. Start by dividing your source voltage, dividing that by the total resistance in the circuit. In this case, the total resistance would be your internal resistance plus the load. So the total current in this circuit is 80 milliamps. Now we're going to calculate the power for the load. I can use any one of the power formulas given in previous lectures to do this. The one I'm going to choose is I squared times R. So take the current, square it, multiply it by the load, and you'll see that the power that is distributed to the load is 320 milliwatts. Now let's change the load to 75 ohms and repeat that process. Begin by finding your total current. Since the load has changed, the total current will also change. Now our total current is 66.67 milliamps. Go ahead and calculate the power for the load using this new current, and you'll see that the power is 333.38 milliwatts. And then repeat this process for the 125 ohm resistor. You'll see that the current is now 50 milliamps when you calculate your total current for this circuit. And then calculate the power distributed to the load. Now the power is 312.5 milliwatts. So if we quickly recap that, when the load was 50 ohms, the power for the load was 320 milliwatts. When the load was 75 ohms, when it was equal to the internal resistance, we had 333.38 milliwatts. And then when the load was 125 ohms, we had 312.5 milliwatts. Out of those three scenarios, we had the largest amount of power distributed to the load when the load was equal to the internal resistance of the source. So here's a graph explaining what we just calculated. As you increase the value of the load resistance, your power will increase until a point. You'll get your maximum amount of power when the load is equal to the source resistance. This was our 333 milliwatts right here. Once you go past this point, the power delivered to the load will begin to decrease. And that is an example of the maximum power transfer theorem. Next, we're going to move on to delta to Y and Y to delta conversions. First, I'll explain what those are. A delta circuit is simply an orientation of three resistors that forms a triangle like this. A Y circuit is an orientation of three resistors that forms a capital letter Y. Notice that letter subscripts are used for a delta circuit, RA, RB, and RC. And number subscripts are used for a Y, R1, R2, and R3. What we're going to do next is discuss how to convert a delta to a Y and a Y to a delta. And then we'll do an application problem that will demonstrate why you'll want to know how to convert between these two forms. There will be times when being able to do a delta to Y conversion or a Y to delta conversion will make your circuit simpler to analyze. So first, to perform a delta to Y conversion, each resistor in the Y is going to be equal to these equations you see on the screen. So let's say that you have a delta and you want to convert it to a Y, which is in green. In order to do that, you have to know the values of R1, R2, and R3. And here's how you're going to calculate those values. So R1 is just RA times RC divided by the sum of all three. R2 is RB times RC divided by the sum of all three. And then R3 is RA times RB divided by the sum of all three. Notice that in order to calculate R1, look where R1 is on the diagram. Look to the left and look to the right. There's your numerator, RA times RC. If I want to calculate R2, look to the left and to the right. There's your RB times RC. And if you want to calculate R3, look to the left and to the right. There's your RA times RB. So even without these equations, if you can remember that relationship, you can very quickly perform a delta to Y conversion. Now let's say that you want to go the other way. If you want to do a Y to delta conversion, each resistor in the delta will be equal to these three equations that you see on the screen. So let's say that you are beginning with a Y, you're beginning with a circuit in green, you want to convert it to a delta form. In order to do that, you'll use these three equations to figure out what is RA, what is RB, and what is RC. Notice that the numerator for all three of these is the same, so you only have to calculate this value once. And then to find RA, we have to divide by what's across from RA. If you go directly across from RA, you're dividing by R2. If you go directly across from RB, you're dividing by R1. And if you go directly across from RC, you're dividing by R3. So these are the formulas that you will use when you want to perform a delta to Y or a Y to delta conversion. Now we'll do an example. The first example is going to ask you to convert the delta circuit below to a Y. So we're going to use the formulas to calculate R1, R2, and R3. Here's the formula for R1, and you're simply just going to plug in the values for RA, B, and C. Here's the formula for R2, plugging in the values again for resistors A, B, and C. And finally, here is the value for R3. Once you have R1, R2, and R3, your next step is to simply draw the Y circuit that you have created. The most important thing about drawing the Y is making sure you know where R1, R2, and R3 go. As a refresher, if this is your delta, where RA is here, RB is here, and RC is here, R1 has to be here. It cannot be over here or over here. R2 has to be here, and R3 has to be here. So you do have to follow that orientation. You can't put R1, R2, and R3 wherever you want to. You have to make sure it lines up with this diagram here. If this is RA, R1 has to be in between RA and RC, and so forth. So using this diagram, you can now draw the new Y circuit that you have created. And that's what it'll look like. Notice that R1, R2, and R3 match up exactly with the diagram. So orientation is very important whenever you're doing a conversion like this. Next, we're going to convert the Y circuit below to a delta circuit. In order to do that, we're just going to use those formulas shown a few slides ago, and we're going to plug and chug the values for R1, R2, and R3 into those formulas so that we can do that conversion. So first, let's begin with RA. Remember, this top number here is something you only have to calculate once, and then you'll use it for all three resistors, RA, RB, and RC. RA will come out to be 9.15 kiloohms. Here's the formula for RB. RB will come out to be 20.1 kiloohms. And here's the formula for RC. RC will come out to be 3.59 kiloohms. Once you've calculated these values, again, you do have to draw your new converted circuit. Don't forget to follow the orientation given. RA has got to be on the bottom left, RB has got to be on the bottom right, RC must be along the top. And there's your delta, showing RA, RB, and RC. So whenever we do a delta to Y or a Y to delta conversion, these two circuits now are equivalent. And you would connect the delta to your circuit in the same way that the Y was connected. So if this is point A in your circuit, this is point A in your new circuit. Point B, point C, and point C. Next, we're going to look at an example of when you would use a conversion like this in order to solve a problem. So let's say that you have the bridge circuit shown below. What we want to do is determine the voltage across the load resistor and the current through the load resistor. And RC is the load. That's the load. So we have to find the current through this resistor and the voltage across this resistor and the bridge circuit below. So what we're going to do is use a delta to Y conversion in order to make this circuit a little bit simpler to analyze. Keep in mind this bridge is built up of two deltas. Here's a delta on the top. Here's a delta on the bottom. Either one of those can be replaced with a Y. And in this case, replacing it with a Y will make it simpler to analyze. Here's how. Notice this is one of the two deltas that you have. If you do a delta to Y conversion, notice that your Y is connected right here. Look closely at how that's connected. This is one point, here's another point, here's another point, and your Y gets connected to the same points. So here's your Y. Once I do that transformation, I can redraw this circuit to give me this. So when considering what you're going to do to solve this problem, what's easier to collapse to find a total resistance and a total current? This circuit or this one? With this circuit right here, no two resistors are in series, so you can't easily add two things together. It's very hard to determine the relationships in this type of circuit. So a delta to Y conversion gives you this circuit, which is far easier to collapse. We can easily see that RD and R1 are in series, RE and R2 are in series, and these two branches are in parallel. Once I combine those two branches are in series with R3. Then I can find total resistance, I can find total current, I can continue on with the problem. So this is where a delta to Y conversion becomes extremely helpful. Otherwise, analyzing this bridge circuit is quite complex. So we're going to take the bottom delta, convert it to a Y, and then continue on with the problem to find the voltage and the current for the load, which is right here. To begin, we'll convert that bottom portion of the delta to a y. So to do that, you need to figure out R1, R2, and R3. Now that you have R1, R2, and R3, you have to redraw the circuit at this point, showing the delta being replaced with the y that you just created. There's what that circuit will look like. Notice that my delta used to be here, like this, and now my y has replaced it. Next, we're going to find the total resistance and the total current in this circuit, and then talk about how we find the voltage for the load resistor. So to find the total resistance, we're going to combine RD and R1. They're in series. Add them up. We're going to combine RE and R2. They're in series. Add them up. Once I add these together and add these together, those two values are in parallel. So I have to find that parallel combination. Then I'm going to add R3 to that number, because when I combine these two branches, those two branches combined are in series with R3. So that's how I'm going to find my total resistance. Now that I have total resistance, I can go find the total current. Going back to the original problem indicates that the source voltage is 12 volts. The source voltage is connected to point A, so I know that 3.56 milliamps comes in here and then splits into two paths. So at this point, we know the total current, we know the total resistance. You may be wondering, though, how we're supposed to find the voltage and the current for RC when RC has disappeared. RC disappeared when we took the delta that was at the bottom and transformed it into a Y. Here's the thing about these conversions. They are equivalent. So the fact that we replace the delta with a Y tells us that this bottom half of the circuit is still equivalent to what was there before. That means the voltage at point C and the voltage at point D are the same voltages with this circuit as they are with this circuit. If I can find the voltage at point C and if I can find the voltage at point D, simply taking the difference of those two voltages tells me the voltage across this resistor. And if I can find the voltage across that resistor, I can find the current going through it. So although RC is gone, we can still compute what the voltage and the current for RC would be by using the same 2 points where RC was connected before. So what we're going to do is find the voltage at point C, find the voltage at point D, subtract them. That would give me the voltage from point C to point D. And that voltage is going to be equivalent to the voltage here from C to D. There's my voltage for that load resistor. So that's our plan of attack. So we have the total resistance, we have the total current. Our next job is basically to figure out the voltage at point C and the voltage at point D. When we say the voltage at point C, we typically mean from C to ground. That means I need the voltage from C and ground is connected after point B. The voltage source would be connected like here. Here's your voltage source. Going to A, going to B. So point B is your ground because that's the path that returns back to the source. So if I have to find the voltage at point C, I basically need to find the voltage along this path. So I need the voltage for R1 and I need the voltage for R3, and I'm going to add them together. If I want to find the voltage from point D, I'm going to also find the voltage from point D to ground. So I need the voltage along this path. So I need the voltage for R1, R2, and R3 in order to find the voltage at point C and to find the voltage at point D. So in order to know those voltages, I need to know the current going through these resistors. So my next step is going to be to take the total current and perform a current divider. So I know how much goes through this way and how much goes through that way. So we're going to find the current through each branch. To do our current divider, we first need to consider the fact that current will flow down to this node and split. We have two paths the current will take. So to do my current divider, I have to know the combination of these two parallel paths. So I have to add these together, and then combine them in parallel, because that number has to be the numerator for my current divider. So that's how I come up with this equation here, where we take each path, add it together, and then combine it in parallel. So then I can find the current from point A to point C by performing a current divider. The numerator of the current divider has to be the combination of my two paths, and the denominator has to be the resistance of the path I want the current for. That path has two resistors, so make sure you include those in your current divider. Same thing for the current from point A to point D. The numerator has to be the combination of these resistors in parallel, and the denominator has to be the resistance of the path in question. Two resistors along that path, so I have to include both of those in the denominator for my current divider. And I get the following currents for the current basically through the left branch and then the current through the right. Now that I know the current through this branch and the current through this branch, I also know the current through R3 has to be the total current because these two branch currents recombine right there. Now I can find the voltage for point C and find the voltage for point D. Here's the voltage for point C. That's going to be the voltage for R1, which is going to be the current through this branch times R1, plus the voltage for R3, which is going to be the total current times R3. And then here's the voltage for point D. The current through R2, which is this branch, times R2, plus the voltage for R3, which is the total current times R3. So I have the voltage at point C and I have the voltage at point D. Again, when we say at a point, it means from that point to ground. So from C to ground, from D to ground, I found these two voltages. My next step is to subtract these two voltages. We're going to find the voltage from point C to point D. Anytime you're finding a voltage from one point to another, you're simply taking the difference between the two. So this gives me a negative 925 millivolt difference. This represents the voltage across the load resistor. That load resistor that is right here in our original diagram. The voltage from point C to D represents the same voltage you would see across that resistor, even though that resistor is no longer in our diagram. Remember, this circuit is equivalent to the circuit that we started out with. So by finding the voltage from point C to D on this diagram, we also find the voltage from point C to D on the original diagram, which is the voltage across that load resistor RC. Now that we have the voltage for that load resistor, okay, so here's our diagram here, going back to where we started. I found the voltage from point C to D on this diagram, which means I know the voltage from C to D on this diagram. These two are equivalent. So I know this voltage now for RC. Now I can find the current through RC by using Ohm's law. Keep in mind, this voltage is negative. All that means is that the polarity is right to left, meaning this is the positive side and this is the negative side. And current flows from D to C because the current is negative. We found the voltage from C to D. It came out negative. that means D is the positive terminal, not C. That's all that means. And that's the current through the load resistor. So this is a great example of how a delta to Y conversion can simplify your circuit and help you to solve a problem that would otherwise be far more complex. And so that's a tool that you now have in your toolbox in order to help you analyze a circuit. And that is the end of this video.